we all know that. And of course, this is induced from a metric. We all know that. The metric is distance between x comma y is absolute value of x minus 1. So that gives you 1. Second example. Well, nothing special about R. You also know Rn. Let me write here Euclidean metric. So gives topological space. Gives topological space. Topological space. More generally, any metric space, if XD is any metric space, we obtain a topology. So consists of open sets. Open sets U contain X. So with respect to the metric D. In other words, what are the open sets? So when do you say a set in a metric space is open? It can be written as a union of open balls. Is that clear? So you have notion of open ball. If any word that I am using is not familiar to you, please ask me because it is for your benefit. If some word that I am using, technical word that you do not understand, please ask me then and there. Don't have to wait till the end of the lecture. So that is U is a union of open balls. Open balls. Let's set some notation. So x epsilon is equal to for y xy is less than epsilon. So this is the notion of open ball. If you can express your set as a union of open balls, alright, maybe epsilon can vary, x can vary, etc. etc. If you can express it in that particular fashion, then you say that the set is open, and you put all such into a bag, call it tau, and that is going to define for you. That is a topology, in the sense that it satisfies the three axioms written here. Alright, so this way every metric space gives you example of a topological space. Okay. But there are many more things, and we will see examples. Of a topological space. So write number 4 or some L. Okay, this example is also in Moncrief's book. I am more or less following Moncrief's book as suggested by Lika, because that's the standard textbooks in many universities. So notations and concepts are all based on that book. What is this? So open sets are, I must each time tell you how to get open sets. Okay, so that is, I must tell you what is my collection tau. Alright, so open sets are unions of intervals A comma B. So A, B, real numbers. Okay, of course it could be empty set also. Empty set and the whole space also I can write. will always assume T set and right. So this, you see, in the usual metric space equation, we will only have, this is not an open set. Like 0, 1 is not an open set in the usual metric topology, metric space topology or R. But here I am throwing in such things also. Okay? And you can see that it will satisfy the conditions that I wrote down. Alright? Very clear. Already I said unions are there. Now I take such things and I take finite intersections. And when I take finite intersections, again it can be expressed as unions of such things. So again they will be open. Right? So this again gives you example of a topology. We will see that this does not come from a metric space, metric on R. We will see that later. Okay, so this space is not metrizable. There is a topology, it doesn't come from any metric. So the study of topological spaces therefore is genuinely much bigger, okay, much more general than the study of just metric spaces. There are also other kinds of examples. One other example which I wish to emphasize is the following. So this time you start with any set X. Let X be a set with a simple order. Which we will write as less than. Sometimes we write less than, sometimes we write less than or equal to. From the context it is clear what is meant. What is a simple order? What is an order? So, see, given any two elements, either x and y, either x equals y, or if x is not equal to y, either x is less than y or y is less than x. So, any two distinct elements are comparable. If that happens, then you so that is the property. The other property is, of course, x less than y, y less than z should mean that x is less than z. Okay? So these two properties, if it holds, you say that this is a simple order. So it differs from partial order only in the sense that in the case of partial order, I could have a situation where x and y are not comparable. Okay, x and y can be elements of the partial order, but here what we have is a situation where any two elements are comparable. Given two distinct elements x and y, either x is less than y. What is the notation here? This is set of all x in x such that a less than x less than b. Okay. Or so, okay, or you write here a naught comma b. This time you put close bracket here. This is equal to set of all x in x such that a naught less than or equal to x less than b, where a naught is the smallest element. A naught is the smallest element of x, or it is of the form a comma b naught close to b naught, where so this is obvious notation x in x such that a less than x less than or equal to b naught, and b naught is the smallest largest element, where b naught is the largest one. So I am going to draw a picture here. There is only one way you can draw a picture. So it is like this, x is like that, this is my x, I choose point A, B and everything in between without including the endpoints. This is the interval A comma B. Or your set X, it is quite possible it has the smallest element. If there is a smallest element, it has to be unique. So that is like A0. It could be like this. A0. So let me do some C could be like this. Or it is quite possible your set has the largest element. Okay? In that case you include that but exclude this. It could be like this. Okay? So these are open intervals. Now how did we get the open sets in all? You said that a set in the real number system is open if it can be expressed as a union of open intervals. Here you do the same thing. The topology, the order topology on X. So X consists of open sets. Open sets. Okay, open sets. Consists of 6, which can be expressed as union of open intervals. So one immediate remark is that the usual metric topology on real number system. You understand? So on the real number system we have metric. I already said that we have usual distance and with respect to which there is a topology. Now on the real number system we also have less than relation, A less than B if B minus A is positive. So that gives you a total ordering on the real number system, and from that you get a topology using this mechanism. Okay, so that gives you another topology. These two topologies are the same because every interval, open interval, is an open ball with respect to its dimension. Okay, so they are one and the same. Why do we have to worry about situations like this? Because your set, open set may be something like the interval 0, 1. Okay? If it is something like 0, 1, then there is a smallest element, namely 0. And in this situation, we would like to say things like 0, 1 by 2, open, this is an open set. And in order to take care of that, we need to have this. Okay? And likewise here. For example, we want to say some 1 by 4 to 1 closed here. This we want to say is an open setting here. Alright? So in order to take care of that, you have to worry about what happens if there is a largest element. In the usual real number system, there is no largest real number. So there you genuinely had only open sets of that form A, B, both sides open. Okay? Clear? We will use these notions many times. You learn examples because suppose somebody asks you a question, open-ended question. Does this space have this property? How do you know that? So you have to go through your collection of spaces, and if you check whether that property holds for all the things in your collection, then maybe you come up with a counterexample. Or if you observe that it's true for all the things you know, maybe it's a theorem. Then you try to prove it. Okay? So it is good to have large collection of different kinds of topological spaces as examples in your kitty. Okay? So therefore you need to. Now there is another object. I do not want to spend too much time on this, but it is an object which is of some importance in topology and it's very much used throughout the book in Monk race. So I will talk about it a bit, not too much but just a little bit. And that is, what is this space called S omega. Those who have taught topology of the Monk race book will immediately recognize what it is. But first let me say a few words about this. So there is this well ordering theorem. Given any set X, it can be well ordered. So what is a well order? Okay. So a well ordering on, well, okay, I start with a simple ordering. Let X be a this time be a total ordering or simple order. Okay, that means X is a set and I have a simple order. Any two distinct elements can be compared. Okay, we say that X is, or we say that this relation is well ordered, is a well ordering on X if every non-empty set A contained in X has a greatest lower has here meaning that greatest lower belonging to X. So, belonging to A. I am writing this to emphasize. Okay? I give you any subset which is not empty, then you must be able to find greatest lower bound. Will become there is only if it exists, there will be a unique one, and that should belong to A. Looks like a very simple property. What are examples of that? Look at natural numbers. I give you any non-empty set of natural numbers, you can find the smallest natural number in that one, and that is your PLD. So natural numbers is a well-ordered set. Well-ordered sets are good for you because you can do induction. If you want to prove a statement by induction, you use well-ordered sets. Usually we do induction using natural numbers. Okay. Integers is not well ordered. Look at negative numbers. There is no greatest lower bound. No matter what element you give, -1 will give you a number which is negative and belongs to that has no greatest lower bound. Okay. So what about real positive non-negative real numbers? So close to interval 0 to infinity. Is it well ordered? No, it is not well ordered. I can look at numbers which are like this: 1 by n, n in natural numbers, n belonging to natural numbers. Okay. This is a subset of 0 to infinity. It has the greatest lower bound, namely 0, belonging to this set, but that itself doesn't belong here. You see what I underline? Belonging to A itself. The greatest lower bound should belong to this subset itself. Is that clear? So this is not a well-ordered set. With the usual well-ordering, this is not a well-ordered set. Okay? So you see, any time you have your set which has you can sort of find a decreasing sequence Okay, each one of which is distinct. I make that as a subset, and then greatest lower bound cannot be there because it's a strictly decreasing sequence. So if you have set the ordered set as a strictly decreasing sequence, sequence of distinct elements which is strictly decreasing, okay, then it cannot, that set cannot be well ordered. Exactly for the same reason why this cannot be well ordered. Okay, is that clear? So this is not a well ordering. There are many other well ordered sets and so on. Just let me give one example. I said it's important to draw pictures in topology. Here is another picture. So I want to give examples of well ordered sets. There has to be the smallest element in my set X. If it is well ordered, the set whole set, let's take X to be non-empty. The whole set must itself have a greatest lower bound. Let us call that some 0 or maybe X naught, whatever, 0. Then it must have, I look at sets of all elements just strictly bigger than this one, that must have a greatest element, that will be something. And then here, they will all have to be sort of separated out, and maybe then somewhere it picks up another, like that. What do we mean by these dots? So, for example, this could be like 0. Okay, let me draw a picture here. It's much easier to draw it. So this can be like a picture of natural numbers. Natural numbers, what is there? So 1 and then 2, 3, 4 and so on. But there is no infinity as such. Infinity itself is not a number, but I just go on like this. Okay? Now, but then I can pick up another number, go on like this. So, and then another pick up. This is how you can build up well ordering. Set with well order. But it's amazing that there is this axiom, more or less. It's called well ordering principle. Given any set, there exists a well ordering. Well ordering on it. Okay. So this is called so in particular you can just take your real number which is uncountable and put a well ordering on it. The picture will be drastically different from the usual picture of real numbers which we draw. Alright? See, if you start drawing a picture of well ordering, that's how it will look like. I said you can call it 0, the next number, whatever it is, the element, you can call it 1, 2, 3 and so on. Well, there is no infinity, but there will be, if it is just not only isomorphic natural numbers, there will have to be something which you may call infinity. But if you call it infinity, this should be called infinity plus 1, and then this should become 2 infinity, and then 2 infinity plus 1, and so on, and then 3 infinity, and so on. Infinity is just a symbol, that symbolically just denote it. Now, if you keep on doing this, you can, imagine that you can just put a well ordering on a countable set. Up to countable set, maybe you can manage to do this by hand. But this is saying that any set, even any set whatsoever, there is a well ordering. So there is a well ordered set of ordinarity just to more than countable, uncountable. There is a, so, and among that you take the smallest consequence, corollary is that there exists a smallest uncountable well-ordered set. And a consequential, so call it omega. Okay. Now this omega is same as that S omega. I have not told you what is S omega, but what do I mean by smallest? So if smallest means the following: if alpha is in omega, then I look at the interval. So there is one smallest element which I decided to call it 0, 0 comma alpha open. Well, this is my omega. Okay, sorry, this is not my omega, this is contained in omega. This is contained in omega. And this is a countable set. So, in other words, if you give me any proper, so this will have to be proper. So, if alpha is in omega, okay, now this, I look at the interval, this is well ordered, this is respect to the same order. This is well ordered and it's a subset of this. I said that this is smallest, so this cannot be uncountable, because if it was uncountable, this will be a proper thing which is contained in here. Alpha is not here by you, so it's a proper subset. So this cannot be uncountable, it has to be countable. Okay? Okay? So this is something we can understand. It will have to look like this in some ways. Okay? What look like what I have drawn above. But S omega, but omega itself, we cannot draw it on a real line. Now, S omega is nothing but omega with given the order topology. This tautological space S omega is the space omega with order topology. Okay. Alright. So this is the important topological space serves to provide counterexamples in many contexts, has very peculiar properties. If you want to understand topology, you should understand what are routine good spaces which behave in ways that you expect. At the same time, you should also have good collection of examples which will serve as sort of warning signals. You may say, look, most spaces have this property, but there are spaces which do not have the expected property. There can be real surprises, and to provide such counterexamples, this space, order, etc. will come in very handy. Okay, is that clear? So in the book, if you look at it, many contexts, in many contexts, this example S omega. I don't know, I lost count. 85, 86. Okay, so here is another way in which you can generate topology. Again, starting with the totally ordered set, starting with an ordered set with ordered topology. So let X, Y, B simply ordered sets, ordered sets with ordered topology. Okay, then so X cross Y has an order, which is the dictionary order. or lexicographic ordering. Okay, so how do you compare two elements? What is a dictionary order? Dictionary order is like if you prepare a dictionary with alphabets from X and alphabets from Y, the order in which the words or letters will appear. Alright? So if I give you X1, comma Y1, I always write order pairs like this to denote elements of X plus Y. So when is this X2 less than Y2? So this happens in the dictionary order. Okay, so all orders will be denoted strictly as. Okay, we will make no distinction. We will not write this sub X 1, 2, nothing. Just this. Okay, so you say when this if, so this is definition, so I will not write even only if, we will simply write if either x1 is less than x2 or x1 is equal to x2 and y1 is strictly less than y2. Okay? Either this condition holds or this condition holds. So you first compare the first letter. You have only two letter dictionary. First compare the first letter. If the first letter here, which is x1, is appearing earlier, then this word will appear earlier in your dictionary. Okay. Suppose the first letters are the same, then you compare the second letters. That's why it's called dictionary order. Okay. Now, and then you put the moment we have now, this is a simple order, one can verify that, because the x and y are simply ordered, therefore x1 cross x2, x1 x cross y with this dictionary order will again be simply ordered. Given any two distinct things, you can compare. Given any two distinct words, either one has to occur first or has to occur later in the dictionary, right? Otherwise it will be one whole big mess. You cannot search for meaning in any dictionary. That's why it's called dictionary order. Now using this, you get the new topology. Alright. So we obtain the order topology. On x cross y. Okay, the induced order. Okay. And we will try to draw some pictures of this in special cases. The simplest, some of the simplest cases that we will understand. Okay, then let us take so example. Take x is equal to the unit interval 0, 1. And x also equal to y. Right? So x cross y, we all know how to draw. So just draw x cross y, which looks like a square. Now what are the open sides in this one? I am going to draw the picture here. So this entire thing is filled in square. Okay? That's my topological space. This is my I2. Now you have to catch up your breath. So give yourself. So what are the basic open sides? Let us first. I mean, if you try to draw all the open sides, there will be union of intervals. But first, how do intervals here look like? Okay. So intervals mean you must give yourself two elements of this. So take 2 points. One has to be less than the other. Okay, that's what total ordering means. So how do I compare? What are the coordinates? Here I write here S. So S comma T. Here S1 comma T1. Here S2 comma T2. Now first you compare the first coordinates. First coordinate, what happens? S1. It's in the x-axis direction. Okay, S1, S2, S1 occurs first. So that means this is less compared to this. And your interval should mean that everything in between is included. But you have to know what are the points that are included. So the moment this is there, everything up above will have the same vertical, they will have the same x coordinate, can be S1, and then t coordinate will be genuinely bigger than T1. So you put a round parenthesis here like that. Now, and then here everything below. Okay, but this itself, this point itself is not included, so indicate it by a round bracket like that. And then everything in between is included. Because everything in between will have S coordinates between these two. So this is one kind of interval. Is that clear? Now there can be another situation. This is, if this alternative holds, there can be another kind of interval where the first two coordinates are the same. S comma T1, S comma T1, and in the same vertical we have S comma T2. Now in this case we just have that, the vertical, the copy of the interval, just looking like that. Is that clear? This is how an interval will look like. These are the basic open sets. Okay, and any open set is union of stuff like that. Is that clear to everybody? Okay. I gave you topology, then I explained to you what are the open sets in here. Is it well ordered? It is not well ordered because you see, I can just choose, remember one criterion or one rule of thumb that I told you. If you have a strictly decreasing sequence of distinct elements, cannot be well ordered. Right? Look here, I just choose this point, this point, this point, this point, this point, and go on like this, but never touch this corner point here. That's a strictly decreasing sequence of points. Okay, what is the greatest lower bound? Greatest lower bound is here, but that itself is not included in your set, so it cannot be well ordered. Okay, you can define order topology whether or not the set is well ordered. You can define dictionary order whether or not the orderings are well ordered. Okay. Now, here is one question. Different, although the components are very much similar. So let us take x to be integers, y to be 0, 1. Okay. Then how will the picture look like? Okay, the picture, so my x coordinate, I must, along the x axis I must draw a picture of integers which will look like that. Okay, this side also. Okay, and now along the y direction there are only 2 points, so this is corresponding to 0 and this is vertical direction 1. So along 1 I get another copy of the integers. Okay. On the other hand, now let us compare. Okay, before we compare, what are the open sets here? The open sets here are intervals again, right? So dictionary order, usual order on integers, usual order on here, 0 less than 1, that's it. Here usual order on integers, you know what it is. So what are the open intervals? Open intervals means first of all you should give yourself 2 points. So just choose 2 points at random here and here. That's all you can do. Okay. Now what are the in between points? In between points means you must. So it's not lined up here properly, but okay. So same x coordinate. So that is here. If this is n comma 0, this is n comma 1, and then here. So this may be some m comma 1. Let us say. Then what happens? So n and then n plus 1 comma 0. That's the next element. And the next element to that is n plus 1 comma 1. And so on. You go on up till here. M comma 0 and m comma 1. Finished. Is that clear? These are the intervals. And what is the topology? In this topology, every singleton is open. Why so? For example, suppose I want to see, of course, if you can see inside open sets here are finite. Yeah, finite sets. And I can take another finite set. Maybe I just choose this and this. So in fact, when I do that, I should omit this, I should omit this. Okay, I should omit those 2 endpoints because interval means I only wrote open interval, so endpoints are omitted. Anyway, any open set, open interval here, any open interval here is finite. Now, if I include, say now I just take, for example, just take n minus 1, 1 and then n 1. Now if I take these two as endpoint, I get only this in the open interval. So that means that singleton is open. So likewise you can see that any singleton here is open. Okay. On the other hand, let us, maybe I should have saved this for exercises or tutorial, but doesn't matter. On the other hand, just want to illustrate what happens if you change the dash. Now I am going to write x is equal to 0, 1, y is equal to integer. Instead of the other way around, I have just this one. What happens now? So this is the type of experiments you should do when you want to learn a new subject. Okay, you learn a new concept. Experiment with basic things. We understand integers. We understand 0, 1. With these as building blocks, create your own questions and do it in the class so students will understand better. You don't need to go to very complicated, very contrived type of example. You don't need to know too much technicalities to bring out the basic concepts. Experiment with simple things which you all understand.